Hey everyone! Today we are going to explore the fascinating ways hydrogen can be prepared. One of the most common methods is through displacement reactions, where metals react with water, acids, or alkalis to liberate hydrogen gas. The type of reaction depends on the metal's position in the reactivity series. Metals that are higher up in the series are more reactive and will displace hydrogen more easily, even from cold water. The general reaction looks like this: metal plus water, acid, or alkali gives hydrogen gas and a salt. This means that the reactivity of the metal determines how easily hydrogen is liberated, and as we move through different methods, we'll see how this plays out in practice. Now, let's break down how metals interact with water, both cold and boiling. When alkali metals like potassium and sodium react with cold water, the reactions are quite violent. For example, potassium reacts with water to form potassium hydroxide and hydrogen gas, as shown in the equation to K plus 2HO to KOH plus H. Similarly, sodium follows suit with a reaction that releases hydrogen gas and produces sodium hydroxide. However, these reactions are so explosive that they're not ideal for preparing hydrogen safely. Calcium, though, reacts more moderately with cold water, and while it's safer, it's still not used industrially due to cost. On the other hand, when we move to boiling water or steam, metals like magnesium, aluminium, and zinc react more slowly but more safely. For example, magnesium reacts with boiling water to produce magnesium oxide and hydrogen gas, Mg plus HO plus H. Steam reactions are much safer and easier to handle, making them the preferred method for industrial hydrogen production. Another common method for hydrogen production involves using dilute acids. When active metals react with dilute acids like hydrochloric acid, HCl, or sulfuric acid, HSO, they liberate hydrogen gas. For instance, magnesium reacts with hydrochloric acid to produce magnesium chloride and hydrogen gas, as shown in this equation, Mg plus to H close MgCl plus H. Zinc, aluminum, and iron follow similar patterns. However, metals like copper, which are below hydrogen in the reactivity series, don't react with acids to produce hydrogen. That's why we often use metals like zinc for lab scale hydrogen preparation. It's efficient, straightforward, and widely used in chemistry classrooms. Now let's move on to how metals react with concentrated alkalis. Certain metals like zinc, lead, and aluminium react with strong alkalis like sodium hydroxide, NaOH, and potassium hydroxide, KOH, to release hydrogen gas. For example, zinc reacts with potassium hydroxide to form potassium zincate and hydrogen gas, Zn plus to KOH KZNO plus H. Aluminium, a highly reactive metal, reacts with both alkali and water, producing hydrogen as well, 12 plus to NaOH plus 2HO to NaLO plus 3H. This method is interesting because it shows the amphoteric nature of metals like aluminium, which can react with both acids and alkalis to release hydrogen. So, while this method is not as commonly used as reactions with water or acids, it's a powerful demonstration of the versatility of metals. Let's get into a specific lab method now: the reaction of dilute hydrochloric acid with zinc. This is one of the simplest and most common ways to prepare hydrogen gas in the laboratory. When zinc reacts with dilute hydrochloric acid, it forms zinc chloride and hydrogen gas, as shown here, Zn plus to H close ZnCl plus H. The reaction is fairly steady and predictable, making it ideal for lab experiments. However, the hydrogen gas produced needs to be purified. Impurities like hydrogen sulfide, HS, and sulfur dioxide, so, can be removed by passing the gas through purifiers such as silver nitrate or potassium hydroxide solutions. The purified hydrogen is then collected by downward displacement of water. This method is easy, reliable, and a standard procedure in chemistry labs. Now, let's take a moment to predict hydrogen liberation based on the reactivity series. We've got four metals here: zinc, copper, magnesium, and iron, and we are reacting them with dilute hydrochloric acid. First, let's look at the reactivity series. Zinc, magnesium, and iron are above hydrogen, meaning they can displace hydrogen from acids. The reactions are simple. Zn plus to H close ZnCl plus H, Mg plus to H close MgCl plus H, and Fe plus to H close FeCl plus H. However, copper is below hydrogen in the reactivity series, so it doesn't react to liberate hydrogen. So, when predicting which metals will liberate hydrogen from acids, always refer to the reactivity series. It's a great way to determine which metals are suitable for hydrogen production. To wrap things up, hydrogen can be prepared through a variety of methods, each suited for different conditions. From reacting metals with water, coal or boiling, acids, and alkalis to the lab method of using dilute hydrochloric acid with zinc, we've seen that the position of the metal in the reactivity series plays a crucial role in determining how easily hydrogen is liberated. While alkali metals react violently and are hazardous, metals like zinc and magnesium offer safer, more controlled methods of hydrogen production. In the lab, using dilute acids like hydrochloric acid on zinc is a common, reliable method for generating hydrogen gas. So, next time you prepare hydrogen, keep in mind the conditions, reactivity series, and the best method for the job.